02.16 tont 08. UTC, Dioscoviar's magnetometer at L1 recorded an instantaneous southward flip of the interplanetary magnetic field and a compressed shock-like jump in solar wind pressure inside a single sampling frame. Across polar latitudes, ground magnetometers rang in unison, a global tap on Earth's magnetic shell. Normally, such a signature follows a coronal mass ejection, the bursting breath of the sun traveling down the Parker spiral. But coronagraphs, which work by hiding the glaring solar disk to reveal outflowing halos, showed no obvious eruption. Solar physicists were divided: stealth CME or something else entirely. Within minutes, alerts lit consoles at NASA, ESA, CNSA, and JAXA. Operators spoke in the shorthand of crisis. Auroral forecasts were revised upward. Radio blackouts bloomed across high-frequency bands. Typically, the script is familiar: Space Weather 101. Yet the absence of a clear solar driver bent that script into a question mark. Enter 3I Atlas, the interstellar comet threading our neighborhood on a hyperbolic path. Normally, comets brighten in a predictable curve as sunlight cooks their ices, their tails tracing gentle arcs in the solar wind. This one resisted the template. Its light curve stuttered, its jets veered against expectations, and spectral measurements hinted at unusually volatile chemistry. Why would an interstellar object behave like this? In observatories from Mauna Kea to La Palma, archival footage rolled. A coronagraph in Chile caught a faint, needle-thin ion tail flaring in a direction models said it shouldn't. Amateur astronomers in South Africa reported a sudden color shift, sodium lines deepening, while a JAXA spectrograph saw a brief surge in ultraviolet emission. Some teams argued this pointed to a dynamic interaction with the heliospheric field. Others doubted the readings entirely. Press rooms filled. Governments explained the first impacts: patchy navigation errors, polar airline reroutes, auroras spilling far beyond their usual borders. Agencies reassured. The storm was strong but manageable. The investigation ongoing. And here's where things take an unexpected turn. A global web of analysts, swarm data from ESA, supermag on multiple continents, radio scintillation from India's GMRT, and solar wind models in Beijing and Pasadena pulled at the same thread. Historical parallels surfaced. The quiet-forged shocks we missed before, the mysteries of Oumuamua, and the dust-rich clarity of 2I Borisov, each a lesson that interstellar visitors refuse our tidy categories. Let's break this down. Earth's magnetic field is a shield. Southward fields crack it open, letting energy pour in. Comet tails, especially ion tails, are not mere streamers of gas. They are electrical conductors draped by the sun's magnetic lines. Could 3I Atlas, by sheer geometry, have shaped the wind that reached us? Plasma theorists floated models: a draped field sheath acting as a magnetic mirror, pickup ions, seeding turbulence, a distant obstacle focusing a shock we only felt at the last moment. Others countered: extraordinary claims, thin evidence. The tension grew with the data. Our models handle solar storms born at the sun, not disturbances sculpted by a traveler between stars. What hidden mechanism could produce such a transition? Moments like this remind us how little we truly understand, yet how quickly a planet can learn when it listens together. And then something even stranger emerged. Vector analysis of the shock normal traced its origin back along the Parker spiral to the precise heliolongitude occupied by 3I Atlas at the minute of impact. 4 minutes ago, magnetometers from Alaska to Antarctica snapped to attention as Earth's field jolted. An interplanetary shock had arrived. Normally, that kind of clean, sudden step is the calling card of a coronal mass ejection, a wave pressed outward by an expanding bubble of solar plasma. A coronagraph works by eclipsing the sun's bright disk to reveal those faint halos. You expect to see a luminous ring, a source, a warning, but this time the halos were timid, the source uncertain, the warning missing. Vector analysis of the shock's face traced its path backward along the Parker spiral. The sun's rotating magnetic winds etched into space, landing on the same heliolongitude where 3I Atlas happened to be. Typically, you'd follow that spiral to an active region or a coronal hole, and call it a day. And here's where things take an unexpected turn. That spiral pointed not at the sun, but at a visitor between the planets. Solar physicists were divided. Some teams argued this pointed to a stealth CME, faint but real. Others doubted the readings entirely, calling it coincidence baked into a tangled magnetic garden. Spacecraft filled in the silence. NASA's Discover and ACE watched the solar wind thicken, the magnetic field twist, then snap past Earth. Spectral measurements tell us more than speed. They hint at composition. ESA's solar orbiter had already tasted a compressive wave upstream, and SOHO's Sky Mapper noted a subtle uptick in hydrogen glow along the same corridor. Normally, a shock's fingerprints match a solar source. This one wore unfamiliar perfume, as if the wind had picked up something along the way. Telescopes tracking 3I Atlas reported a muted flare and a thin, asymmetric coma. Normally, comets brighten in a predictable curve as sunlight bakes their ice. This object hesitated, then sighed, a stutter of dust and gas with a spectrum richer in carbon chains than expected. Some teams argued this pointed to mass loading. Neutral atoms shed by the object get ionized, mix into the solar wind, slow it, and steepen a passing wave into a shock. Others countered that a body so small cannot yank space weather by the collar. The world responded in chorus. NASA, ESO, CNSA, and JAXA toggled instruments into high cadence. Parker Solar Probe's latest pass was reprocessed. Overnight, Hinode and Kwafu 1 scanned the suspect longitudes, while Stereo hunted for the faintest halo. Amateur radio networks logged sudden ionospheric fades. Multi-continent telescope arrays stared at a speck against the sun's breath, listening for a pattern. To understand why this matters, we need to look at our history. This echoes the mystery of Oumuamua, an object that refused our categories, and the quiet debates over stealth CMEs we've argued about for years. Why would an interstellar object behave like a valve in the solar wind, opening and closing pressure with a whisper of gas? What hidden mechanism could produce such a transition? Moments like this remind us how little we truly understand, yet how quickly a planet can learn when it listens together. And then something even stranger emerged. A sudden jolt rippled across Earth's magnetometers just minutes ago, a crisp step in the needle that space weather forecasters call a sudden impulse. Normally, these come when a coronal mass ejection, or a high-speed stream, slams into our magnetic shield. Satellites stationed upstream give us a heads-up. The bow shock flexes, the ionosphere hums. But this one arrived without the usual trumpet. No obvious halo in the coronagraphs. No classic plume arcing from the sun. A confusing silence met the coronagraphs. A coronagraph works by hiding the sun's bright disk so faint coronal structures can be seen, tracing ejected plasma as it escapes. If a CME caused this, we should have seen a luminous bubble, or at least a faint, ragged front. Instead, we saw subtle streamer kinks, hard to interpret. Solar physicists were divided. Some teams argued it pointed to a stealth CME, an eruption so gentle it left only whispers. Others doubted the readings entirely, suggesting a co-rotating interaction region where fast wind overtakes slow and compresses space like a moving weather front. An alignment map complicated things. The shock's orientation, reconstructed from multiple satellites, pointed close to the heliographic longitude where 3I Atlas had crossed the solar wind earlier. Normally, a comet-sized body only drapes field lines and carves a tiny cavity, a local bruise in a vast flow. But 3I Atlas isn't normal. Spectral measurements tell us its gases are rich in supervolatiles and dust unlike most comets we know. Why would an interstellar object behave like a valve in the solar wind, opening and closing pressure with a whisper of gas? Observatories compared notes in real time. NASA's Discover saw a pressure jump, ESA's solar orbiter recorded a tweak in the magnetic spiral, JAXA's Hinode tracked coronal flickers, and China's ASOS skimmed the sun's lower atmosphere for clues. Amateur radio operators reported brief fade-outs along the terminator, a telltale of ionospheric stirring. Some teams argued this pointed to a chance coincidence. The sun was primed to snap anyway. Others saw the timing and geometry and asked, carefully, Did 3i Atlas nudge a stressed system over the threshold? A curious brightness flicker returned to the object itself. Normally, comets brighten in a predictable curve as sunlight warms their ices. But 3i Atlas pulsed. On, off, then on again. Let's break this down. If pockets of exotic ice vent suddenly, they can expand the coma, load the magnetic field with fresh ions, and momentarily stiffen the flow, like a curtain catching wind. As outgassing subsides, the curtain falls, and the pressure relaxes. A tiny actor, big stage. History offers echoes. Oumuamua taught us that not all interstellar visitors follow the rules. Borisov showed us one that did. We haven't seen something like this since. An object possibly modulating space weather, not by brute force, but by timing and texture, slipping into the sun's rhythm like a syncopated beat. To understand why this matters, we need to look at thresholds. Earth's magnetic shield is a living boundary, poised, balanced, and exquisitely sensitive. It doesn't take a hammer blow to make it ring. Sometimes a fingertip will do. What hidden mechanism could produce such a transition? Did 3i Atlas simply arrive at the wrong moment, or the right one? Moments like this remind us how little we truly understand, yet how quickly a planet can learn when it listens together. But this was only the beginning. 4 minutes ago, magnetometers from Reykjavik to Canberra twitched in unison, a sharp geomagnetic shock pressing against Earth's magnetic cocoon. Normally, that kind of sudden impulse rides in on the bow wave of a coronal mass ejection, the natural pulse of the sun. But coronagraphs showed no classic Earth-directed halo, no luminous snowstorm racing toward us. And here's where things take an unexpected turn. At the L1 gateway, the Space Weather Sentinels, Discover, ACE, and SOHO picked up a jump in solar wind pressure and a quick twist in the interplanetary magnetic field. Usually, those are the fingerprints of a routine solar shock. This time, the timing lined up with a different suspect. The Parker spiral field line connected to the sector of space where 3i Atlas's ion tail was drifting. Solar physicists were divided. On the sun-facing cameras, the story seemed incomplete. A coronagraph works by blocking the sun's blinding disk to reveal faint structures in the corona. If a CME is coming our way, it blooms outward like a ghostly ring. Instead, only a thin streamer teased the edge of the field. Some teams argued this pointed to a stealth CME, subtle, low contrast, easy to miss. Others doubted the readings entirely. Across the radio spectrum, amateur observers noticed the sky change character. VLF beacons jumped, shortwave paths bent, a classic sign that the ionosphere had been jolted. Normally, this is what you expect when solar particles stir the upper atmosphere, but the impulsive signature was brief, crisp, more like a tap than a shove, suggesting a compact shock. Front. Inside the magnetosphere, NASA's MMS and ESA's cluster recorded a paper-thin current sheet snapping past. Typically, that means the solar wind has delivered a clean boundary. This boundary, however, rippled with turbulence, as if seeded by something filamentary drifting upstream. JAXA's Hisaki glanced earthward in ultraviolet, while ESA's swarm traced the geomagnetic wiggle from pole to pole, a planet listening together. Meanwhile, ground telescopes and the UH-IFA Pan-STARRS network tracked 3i Atlas's tail brightening in sodium light. Spectral measurements tell us what atoms glow. Sodium sings in a narrow yellow band. Usually, cometary sodium is modest, a whisper on the wind. Here, it flared. Some suggested an unusual mix of interstellar salts feeding a long, fragile tail. Others cautioned, twilight contamination can mimic a sodium surge. To understand why this matters, we need to look at how the solar wind carries influence. The sun's magnetic field spirals outward like a rotating lawn sprinkler. If a comet's ion tail connects to Earth's magnetic footpoint along that spiral, disturbances can travel far, fast. We've seen echoes of this before. In 2007, Comet Encke's tail was cut clean off by a passing shock. But turning that around, an object helping deliver the shock would be new. At mission control centers from NASA to ESA's Space Weather Service, from CNSA's monitoring stations to JAXA's science rooms, The debate lit up. Some teams argued this pointed to a foreshock enhancement channeled by a cometary plasma sheet. Others said a coronal hole's high-speed stream simply arrived early. Caution battled curiosity. In real time, why would an interstellar object behave like this? If 3I Atlas carries unfamiliar chemistry, it could shed ions that hitchhike on the solar wind, laying a conductive thread across space. If so, even a faint solar twitch might pluck that thread, and Earth would hear it. Moments like this remind us how little we truly understand, yet how quickly a planet can learn when it listens together. And then something even stranger emerged. A sudden tremor swept through Earth's magnetic field just minutes ago, a worldwide ping recorded from Alaska to Australia. Normally, such a global jolt follows the arrival of a clear solar shock, an eruption seen leaving the sun, mapped across space, and predicted hours in advance. This time there was no obvious herald, and here's where things take an unexpected turn. Solar coronagraphs stared at a calm-looking star. A coronagraph works by placing a tiny disk over the sun's bright face, revealing faint halos of plasma around it. In those images, no classic, billowing coronal mass ejection appeared, only a subtle nudge of a streamer, a whisper rather than a shout. To understand why this matters, we need to look at what else the instruments saw. Upstream monitors at the L1 point, Discover and ACE, caught a quick rise in density and magnetic pressure, the calling card of a shock front. Normally, the ion mix looks familiar, protons leading, with steady traces of helium and heavier atoms. But the ion spectra hinted at a skew in the heavy ion blend, a faint deviation that raised eyebrows. Spectral measurements tell us about charge states and composition. Today, they suggested something slightly off-template. Telescope arrays tracking 3I Atlas, the interstellar visitor, reported a thin, variable ion tail arcing along the Parker spiral. The sun's magnetic field wound like a garden hose by rotation. Amateur astronomers from Spain, South Africa, and Japan independently caught the tail changing direction in step with a solar wind shift. JAXA's Hisaki saw a softening in Earth's auroral emissions. ESA's solar orbiter logged a local ripple, while NASA's Parker solar probe, deeper in, recorded turbulence but no clear culprit. The choreography was global and oddly aligned. Solar physicists were divided. Some teams argued this pointed to a co-rotating interaction region, an ordinary compression zone that just arrived quietly. Others doubted the readings entirely, calling them calibration ghosts. And a bold few suggested pickup ions shed by 3I Atlas could have threaded a conductive path along magnetic field lines, priming Earth's space weather. Let's break this down. Pickup ions are neutrals that get ionized and swept up by the solar wind, joining its electric dance. Normally, their effect is local and small, but if an interstellar object is unusually rich in exotic volatiles, those ions can travel far, altering how shocks steepen and propagate. Why would an interstellar object behave like this? History offers echoes. We've seen comets suffer tail disconnection events when shocked by solar gusts, and we watched Oumuamua bend expectations about how small bodies move. We haven't seen something like this since, well, we haven't really seen this at all. If 3I Atlas can seed the wind with unfamiliar ions, then it doesn't just pass through our system, it writes in it. Moments like this remind us how little we truly understand, and how quickly a planet can learn when it listens together. The shock has passed, the debate has begun, and the sky is not done speaking. A sharp jolt hit Earth's magnetic field, a clean step in the magnetometers that forecasters call a sudden impulse. Normally, that means a coronal mass ejection has arrived, heralded by bright arcs in solar images. This time, the warning was only minutes long. The sun looked oddly quiet, and upstream monitors mumbled about unusual composition. Scientists began whispering the same name, 3I Atlas. Coronagraphs from NASA and ESO showed just a ghostly puff along a streamer. A coronagraph works by blocking the sun's glare so faint solar wind structures stand out. Big eruptions look like luminous bubbles. Here, there was no bubble. Solar physicists were divided. Some teams argued for a stealth CME, small, fast, and easy to miss. Others pointed to a solar wind altered by pickup ions, like dye dropped into a river. Could 3I Atlas be the dye? Spectral instruments told a stranger tale. Spectral measurements tell us what atoms and ions are in a flow by the fingerprints of light they emit or absorb. Normally, the solar wind's recipe is well known, but Solar Orbiter, ACE, and CNSA's ASOS reported skewed heavy ion ratios and cooler charge states embedded in a hot stream. JAXA's Hisaki saw a brief shift in Earth's oxygen glow when the shock arrived. Skeptics doubted the calibrations. Cross-checks tightened, the anomaly held. On the ground, magnetometer arrays blinked from Scandinavia to New Zealand, while amateur radio operators reported sudden fades and then a clear, ringing ionosphere. Normally, storms swell and relax over hours. This one snapped on, then threaded into narrow arcs. Multi-continent telescope arrays, including ESA and NASA partners, watched 3I Atlas's tail flicker in the same window. Coincidence? Or a chain? Farther out, Parker Solar Probe and Bepi Colombo caught the ripple upstream, letting teams triangulate its path like listening posts. To understand why this matters, we need to look at how timing works. When two spacecraft feel the same wave at different times, you can trace its direction and speed. ENA imagers, which turn neutral atoms born in charge exchange into sky maps, hinted at a faint spray aligned with 3I Atlas's wake. Others saw patterns in clouds. And here's where things take an unexpected turn. If interstellar dust and gas from 3I Atlas were ionized by sunlight and swept into the solar wind, they could act as pickup ions, fresh riders that change the wind's weight and rhythm. That could steepen a modest wave into a shock right at Earth's doorstep. Why would an interstellar object behave like this? What hidden mechanism could produce such a transition? History offers a compass. Oumuamua defied our expectations. Borisov reassured them. 3I Atlas might be teaching us that interstellar visitors don't just pass through. They can tune the medium we all share. Moments like this remind us how little we truly understand, and how quickly the world can learn when NASA, ESA, CNSA, JAXA, and thousands of amateurs listen together. But this was only the beginning. 4 minutes ago, magnetometers from Alaska to Antarctica snapped upward in unison. A sudden impulse, the hallmark of a shockwave striking Earth's magnetic shield. Normally, these jumps come with plenty of warning from upstream monitors. This time, the alarm was late, and the question surfaced instantly. Did 3I Atlas just tune the space weather around us? Earlier today, coronagraphs aboard SOHO and Stereo recorded a faint streamer blowout, a narrow puff along the sun's equatorial belt. A coronagraph works by blocking the blinding disk to reveal the faint outer corona. Most such puffs barely graze our forecasts, but this one crossed the wake of 3I Atlas and, according to several teams, came out the other side sharper, faster, more organized. Hours before impact, Parker Solar Probe and ESA's Solar Orbiter sampled a pocket of heavy, sluggish wind laced with odd pickup ions. The fingerprints of neutral gas suddenly ionized and swept into the solar flow. Normally, that signature hints at a comet. Here, the spectra suggested exotic volatiles seen around 3I Atlas, mass-loading the wind and draping magnetic field lines like a cape. At Earth's L1 Sentinels, NASA's DS-COVER and ACE caught the flip to southward BZ only minutes before the ground impulse. BZ, the north-south tilt of the interplanetary magnetic field, is the switch that opens our magnetosphere. Southward is the key that fits the lock. Usually we see that switch coming. Today it arrived as a thin, patchy front, hard to forecast, impossible to ignore. Within moments, superdarn radars showed convection cells surging sunward, GNSS receivers reported scintillation, and grid operators quietly shifted load. JAXA's Arase saw the inner magnetosphere compress. CNSA's Fengyun satellites logged an abrupt particle spike. The magnetosphere did what it must. It bowed, it reconnected, it rang like a bell. Across the community, solar physicists were divided. Some argued this was a co-rotating interaction region, nothing to do with an interstellar traveler. Others pointed to mass loading and magnetic draping by 3I Atlas as the amplifier that turned a minor puff into a focused shock. Skeptics countered, correlation is not causation. Why would an interstellar object behave like a space weather lens? On the ground, amateur radio nets crackled into dropout and then returned under a soft auroral hiss. Daytime auroras flirted with mid-latitudes, brief and pale. Normally such displays wait for night and stronger storms. Today they arrived on a knife edge of timing, as if someone nudged the dials. Historically, we've watched comets reshape plasma, Encke's tail severed by a CME, Halley's bow shock tasted by Giotto, Oumuamua's unaccountable push rewriting expectations. But we haven't seen an interstellar body implicated in a geomagnetic shock at Earth. If wanderers can tune the medium we share, what else are we missing? Moments like this remind us how little we truly understand, and how quickly the world can learn when NASA, ESO, CNSA, JAXA, and thousands of amateurs listen together. And then something even stranger emerged. 4 minutes ago, Earth's magnetic field rang like a bell. Magnetometers from Alaska to South Africa logged a sudden impulse, the signature of a shock sweeping past. On our screens, the only CME looked too small and off-angle. Normally, that's enough to dismiss a link. And here's where things take an unexpected turn. At L1, Dieskova saw a density spike and the interplanetary field flip south. Textbook storm setup. But Solar Orbiter had already flagged an excess of pickup ions, including sodium, and CN fragments more at home in a comet's breath. On coronagraphs from SOHO and Stereo, a faint halo crept outward. A coronagraph works by hiding the sun behind an artificial disk so the dim cloud around it can be seen, and by energy alone, this cloud should have brushed us with a nudge, not a slap. Across the world, amateur spectroscopists had been tracing 3I Atlas's unusually straight sodium tail near the Sun-Earth line. Normally, comets brighten smoothly. This one's light curve stuttered, and the tail behaved like a conductive ribbon draped on the solar wind. Scientists began to test a provocative link. If neutral gas from 3I Atlas was ionized along our line of sight, it could seed a pickup ion sheet. Freshly ionized atoms caught and accelerated by the solar wind, lower local Alfvén speeds, the speed of magnetic ripples, and let the CME's weak wave steepen into a sharper shock. Solar physicists were divided. Some teams argued the physics checks out in principle. Others called it coincidence, noting small bodies shouldn't drive global storms, even indirectly. Global instruments weighed in. JAXA's ARAS heard chorus waves right after the impulse. ESA's SWARM mapped current surges, and SuperMag lit up while amateurs forwarded spectra from Chile, Iran, and New Zealand. This echoes Encke's tail disconnection in 2007 and the puzzles of Oumuamua. Yet we've never seen an interstellar visitor even tentatively tied to a geomagnetic shock. What hidden mechanism could turn a passerby into a tuner of space weather? Spectral measurements tell us what atoms are present by their color fingerprints. But the path from atoms to aurora is long and tangled. Moments like this remind us how little we truly understand, and how quickly we learn when NASA, ESA, CNSA, JAXA, and countless amateurs listen together. If confirmed, the implication is simple and profound. Interstellar objects don't just cross our sky, they can briefly sculpt the medium we share. But this was only the beginning. The models are loading, and the night side is turning to face the storm.